Hey guys, welcome back to MSE 6765. This week we're talking about strengthening mechanisms in plasticity. This builds on last week's lectures where we talked about the stress field around dislocations and interactions with dislocations. And we talked about the Pech-Kohler force, Pech-Kohler equation, which allows us to describe the force acting on a dislocation given a stress, and that controls dislocation interactions. Today we're going to talk about dislocations interacting with other obstacles that form impediments to slip. And we'll break this up into four parts. Today we'll talk about general obstacles and dislocations interacting with other dislocations. Talk about dislocations in the second part, dislocations interacting with grain boundaries, how a solid solutions strengthen alloy, how alloys and atoms in solution can contribute to strengthening, and then the last part we'll talk about particle strengthening. So every time we think about strengthening, I want you to repeat this over and over again. The strength of a crystal is increased by the obstacles that restrict dislocation motion. Everything to do with the yield strength of a material, of a crystal, is directly tied to how hard it is to move dislocations through that material. Right? The pyrrole stress is an intrinsic kind of strength, right? That depends on the lattice. Now we're going to be adding additional things and put additional things in the way to make it harder to go. And we need to consider when we're moving dislocations around things, we need to remember our line tension of a dislocation, right? Remember, this is the stress required to bend a dislocation to a given radius, right? Because as you bend a dislocation, you're creating more dislocation line length, right? So there's a natural force to reduce the line length by making the dislocation straight. But we have by applying a stress, we can bow that dislocation out. So if we consider obstacles, right, that have some space, effective space between them, L. We'll talk about an effective spacing L prime. We'll talk about the difference between L and L prime a little bit as we go on. But let's consider a strong obstacle. So we're going to say this effective spacing is about the distance between the actual physical distance between the obstacles. And if a dislocation comes up on this array of obstacles, it's going to bend around them, right? And it's going to bend, and they're going to keep bending and bowing out until there's some critical angle that's met here, and then it'll break through, right? If these are very, very strong obstacles, our critical effective length is the actual physical length between them, and this critical angle goes to 0, and then we bow around. If they're not perfect obstacles, there's going to be some critical angle, right? And we end up with a shear stress that depends on, that looks like this, right? This effective obstacle spacing and the critical angle are the key parameters here, right? So the most you can do is GB by L, right? If we consider a strong obstacle, something that this critical angle is small, right? We have an angle that looks, expression that looks something like this. Now imagine we have a weak obstacle, right? L here is in our previous expression, is this actual physical distance between obstacles, right? The nearest direction, right? This is L here. But we said we really need to consider L prime. What's the effective length? So for a dislocation, we can imagine a dislocation line that's pretty straight, right? And if we make this, if we draw a random line through our sample, the average distance along a given intercept between obstacles is L prime, right? So that's going to be closer than the nearest distance to distance here, right? It's just length along a line. So just take a piece of paper and slap it up on your notes, right, in any direction, right? And the distance between dots along the edge of that length of the piece of paper we'll call L prime. Now these are weak obstacles, right? So the angle is pretty small, right? It's close to 180 degrees or pi, right? It's not going to bow around them very much. And we can work through it, right? This is just the relationship between the nearest neighbor distance and L, right? This is just geometry. And if we plug that into the expression on the previous slide, and we replace L prime with L, we get this strength for weak obstacles, right? And so notice we're now raising this cosine term to a power that's more than 1. So that's going to reduce this faster, right? This is going to be small. This part here is going to be smaller than if it was for a strong obstacle. Okay. So dislocations can act as obstacles to other dislocations, right? And dislocations can either act as hard or soft obstacles, right? And we know that when this is a single, the deformation of a single crystal sample, we know we have our elastic regime, a regime where there's not much happening, right, where our plastic stress strain curve is pretty flat, and then a region of increased hardening, right, and then a region where we start to saturate again. So these are broken up into stage 1 or easy glide, stage 2 and stage 3. We'll talk about stage 2 and stage 3 in just a little bit. So in easy glide, right, what little hardening you have is due to the motion of dislocations that are on their parallel slip planes, right? The obstacles correspond to regions of fluctuation, right? They're all dislocations lying basically in the same slip plane. They're weak obstacles, all right? Right, small interplanar spacing and higher dislocation densities result in greater strengthening. But there's only weak obstacles, right? It's other dislocations lying in the same slip plane. When we get to stage 2, now we start seeing dislocations that act as hard obstacles, right? If we activate multiple slip systems in a crystal, those slip systems intersect each other. So the dislocations on those slip systems hit each other at oblique angles, right? They're not parallel anymore. And those intersections lead to immobile jogs or other types of dislocation locks, right? And those have to be circumvented either by bowing or extrusion. And so they act as hard obstacles. Okay? So if we assume that all dislocations represent obstacles, right? If our dislocation density is rho, right, then our obstacle spacing is going to be given by L squared rho. This is some constant. And you'll play with this expression for homework a little bit. But we end up with this relationship. Tau is tau naught plus alpha GB rho to the 1/2, square root of the dislocation density. This is the Taylor hardening relationship. It's a very kind of well-known, important relationship that basically says your yield stress is proportional to the square root of your dislocation density. Right, where tau naught, this is the intrinsic strength of a material with low dislocation density. Right, this is given by the pyral stress convolved with the number of dislocations that you have. Right, this is kind of the initial yield point here. And alpha is a geometric factor that depends on the crystal structure. Right, it's significantly less for FCC than BCC or other materials. Right, okay, so here is just a play out of that square root rho, the square root dependence of the dislocation density. Right, so here is the dislocation density over several orders of magnitude, right? Okay, 10 to the 12th is kind of your average well-annealed polycrystal, right? 10 to the 10th is an amazingly clean sample. Very, very few dislocations. 10 to the 15th, this is heavily cold worked material. So a huge amount of dislocations here. And so basically this represents the range, the entire physical range of dislocation densities that you can get in copper. And we see this square root rho behavior across that whole range. Right, so this is an important thing. In class, I mentioned, my rules of thumb. Right, this should be one of your rules of thumb. Yield strength, Taylor hardening, square root rho. Okay, so where does this square root come from? Right, so at low strains, the dislocations are more or less homogeneously distributed in your sample. Right, that the spacing between defects, the spacing between dislocations is basically 1 over their dislocation density. So the pinning strength is going to be a proportional or about GB square root rho. At higher strains, dislocations become localized and are heterogeneously distributed into a cellular structure. Right, we'll see pictures of it on the next slide here. But inside the cell, the dislocation density is very low. But the cell walls consist of links of tangled dislocation lines meeting at nodes, right? And extrusion takes place right between the longer links in the wall. So we can relate the cell size D to, oh, dang it, this should be the yield strength, right, with a relationship like this, right, where D here is going to carry the square root. This K prime by D, this is a Hall-Petch-like, this is the Hall-Petch-like parameter, and this is going to carry our dependency on the dislocation density. Sorry. So our K prime increases with increasing plastic strain, and our D parameter is going to saturate at large strains, right? This is our stage 3 hardening, right? In FCC metals, our cell size, D, eventually stabilizes, right? And that's what we call the onset of that stage 3 hardening, if we go back here, right? So in a single crystal FCC, our dislocation, here we have dislocations that are growing, but basically they're all parallel. Stage 2, now we're activating multiple slip, we're getting dislocation interactions, and our dislocation substructure is evolving. And we go from a bunch of parallel dislocations on the same slip system to a bunch of intersecting dislocations to a complex dislocation substructure with a bunch of tangled cell walls that contain a huge number of dislocations and relatively dislocation-free little crystallites in the middle. And that's at that stage we're at the beginning of stage 3. Excuse me. Okay. So we'll talk a little bit more about these cell wall structures in class, but they represent a minimum energy configuration, right? It's less energy overall for dislocations to form these arrays of cell walls than to be homogeneously distributed through the matrix at a high in high energy configurations, right? The higher the stacking fault, the narrower walls, and the more dislocation-free the interior. At lower stacking fault materials, we get more diffuse walls. And you can see this here in aluminum, where you have very high, large stacking fault. These are dislocations. These are subgrain boundaries, right? These are dislocation cell walls, and inside we don't see any defects. Whereas in copper, you can see the cell walls are more diffuse, and we still see more dislocations inside the interior. Right? And if we go to very, very low stacking faults, we end up with these. We get planar arrays of dislocations rather than even a cellular structure. Okay, we'll stop there, and we'll pick it back up with grain boundary strengthening in a couple minutes.